Hello, my name is Ronakostam Desh. Today I am presenting Zenith OS, a kernel resource and process monitor for this project. My goal was to create a visually satisfying and technically accurate simulation of how an operating system manages the life cycle of processes and the allocation of critical system resources. So here I used Colorama preset and everything. I used Python code because it's easier for me to code in it. These are the code, these are the simulation logic, process table section, and this actually works for me as a OS scheduler. This loop identifies if the process needs to be on the ready queue or the running queue. And if we go to the actual terminal here and if we run this code, uh, here I have developed a terminal user interface. In a real world scenario, a kernel needs to monitor health matrices constantly. At the top here we have the CPU load and memory usage here, and then we have the active process queue, which actually contains PID, the process name, and most importantly the state. I mean, if I run it again, you can see that it's actually changing from ready queue to running queue. Here there's a ready queue and it just transforms into running queue. It's real-time data, so it transitions actually. Then comes to the deadlock part. Let's look at the bottom dashboard. You can see the kernel logs recording every state change. As we reach the final process, the system identifies a resource contention here. So because of the resource contention, we see a kernel panic. If we see closely, 9901 network daemon is blocked here because it discovers a deadlock. And a deadlock is where a process is waiting indefinitely actually for resources held by each other. So through Zenith OS, I have combined process management system, process management theory with a clean functional UI. This project highlights the core fundamentals of state transition, resource management, and fault detection. Now, there are few technical justifications actually why I didn't actually use real-time data. The first reason is cross-platform portability and stability. Accessing real-time kernel-level hardware data often requires platform-specific libraries and elevated demonstrative permissions. By simulating these values within the software logic, the project remains completely portable. It is guaranteed to run the identity, it is guaranteed to run on every single OS, Mac OS, Microsoft, Windows, or Linux, everything. So it's user-friendly. And then comes the second part, which is scenario-specific stress testing. Like real-time data is often unpredictable. To demonstrate the deadlock detection and kernel panics effectively for a graded academic project, the system must reach critical thresholds. Like if I uh, if I took real-time data, I couldn't actually print this blocked and this 99% CPU load because I can't actually put my PC or my Mac into risk by doing that. So that's why I had to force a deadlock here. This is where I am actually forcing a deadlock, and that's how I can show you why a deadlock is happening and not. And the third reason is system integrity. Forcing a real deadlock or a memory overflow on a physical machine can cause the host OS to hang or crash, potentially leading to data loss. Zenith OS provides a high fidelity environment to study these critical failures within a sandbox, allowing for the observation of OS theory in action without risking the health of the hardware. Like we're not actually risking the health of the hardware, but we're actually being able to see the OS theory and everything. So this was my project. This is called the Zenith OS, and thank you for watching.